Hello again, and welcome to another review session for your final exam in Calculus 3208, presented by CBL Live. And we're still in the guise of the calculus of trigonometry here. And in this session, we're going to get right down to how do we find the derivatives of our regular old primary and reciprocal trig functions. So let's get started on that. This is lots of fun. Okay. So stuff we're going to focus on, we're going to use the definition of the derivative to figure out the derivatives of sine and cosine. Now, for your final exam from your own class, your teacher may have told you that you're not responsible to know how to do those, but you never know, it might show up on the CPT anyway, so they're worth going through. And the second one says we're going to compare the graphs of sine and cosine with their derivatives, so we can sort of verify to ourselves why these things make sense. And then we're going to use the derivatives of sine and cosine, along with differentiation rules, to find the derivatives of the other four trig ratios. Here we go. So the first thing is, how do we differentiate f of x equals sine x? How do we find that derivative? So we're going to get right back to our definition. So here's the definition of the derivative that we all know and love. F prime of x is f of x plus h minus f of x all over h as the limit as h approaches 0 of that. So let's see what happens. We're going to change our f of x, of course, to be sine x in this case. All right. So if f of x is equal to sine x, we get this monster over here, sine of x plus h. And that's really the key for us to get through this. You should know from your trig identities that you learned in your other grade 12 math course, your 3200 course, that the sine of x plus h, well, you can look at it as a plus b or alpha plus beta, whichever way you're used to saying that, but the sine of x plus h is actually an identity that would be sine of x cosine h, right here, plus cosine x sine h. So all we've done in that first step is we've replaced this with that expansion based on the identity. Okay? Then in the next step, all we do is we take the second two terms that we have in the numerator there, and we're just going to swap the order. So we're going to write them in the other order. So all I'm doing there is I'm just taking this term right here and this term right next to it, so these two terms, and we're just going to switcheroo and put them in the other order. Okay? Then, based on what we have in that line, we're going to look at the first two terms we have now and notice that we have a common factor there of sine of x. So I remove the common factor of sine x, and the two terms I have left over will be cosine h and negative 1. Okay? So then it's time to start splitting up our limit. So right at this positive sign, I'm going to take this and I'm going to break it into two separate fractions that are a sum both of the same denominator of h, okay? And we have, since we have the limit of a sum, we know that that's going to be the sum of the limits. All right, so I've got two separate limits now. For that first limit, notice that our variable that's changing here is h. We're talking about a limit as h approaches 0. Well, what's going to happen to sine x as h approaches 0? Absolutely nothing, because sine x doesn't depend on h at all. So we're just going to take the sine x and throw it out front. And then in the other limit, we're going to do the same kind of thing with cosine x. Since it doesn't depend on h, we're just going to throw it out in front down here. So what you see now we have is sine x times a limit that we should recognize, plus cosine x times another limit that we should recognize. So this first limit we know should be equal to 0, so we have sine of x times 0. And the second limit is equal to 1, so we have cosine x times 1. So this first term will be equal to 0, we don't need it, and we just get cosine x. So an algebraic proof then of the derivative of sine x tells us it should be equal to cosine x. All right, let's try something similar for cosine. So I want to differentiate cosine using the definition of the derivative as well. So we'll start with the limit as h approaches 0, blah, 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 definition. And then we're just going to change f to cosine x. All right, so we notice that we have something over here that we have an identity that we can use to manipulate. So our identity for that one says it should be cosine x cosine h minus sine x sine h. Okay? And once we have that established, sort of similar to what we did in the last one, I'm going to take my last two terms that I had. So I'm going to take the term that is this one and the one next to it right here, these two, and I'm just going to switch their order like that. Okay? So after I get their order switched, then all I have to do is look at the first two terms that I have now in my fraction on the numerator and say they have a common factor of cosine x. So I factor that out. And then what I'm going to do is, right at this negative sign, I'm going to throw an x through my fraction and split it into two fractions that are added together that would equal the same thing. And then I know that the limit of the difference is the difference of the limits. And so I'm going to take each of those two limits that I have and remove the part that doesn't depend on h by throwing it out in front of the limit in both cases. So I get this limit and this one. So I also recognize now that this limit should be equal to 0, and this limit should be equal to 1. And if that's the case, I have cosine x times 0, which is 0, minus sine of x times 1, which is negative sine of x. So the derivative of cosine is negative sine. All right, lots of fun. Why does it turn out that the derivatives of the first two trig functions that we know about are actually very close to being just one or the other, the derivatives of each other? Why does that happen? Well, let's see if we can justify that a little bit. We've already proven it, but let's get a conceptual understanding of what's going on here. If I look at y equals sine of x, I've graphed that in blue on the first graph, and we already said that its derivative, dy over dx, should be cosine of x. Well, I'm going to first just draw some tangent lines at all of the vertices, or the maxima and minima, of y equals sine of x. And what I'm noticing is at all of those places I have horizontal tangent lines, which is something we should know. And then if I look at cosine x is equal to 0 there. So it stands to reason that it's possible cosine of x could be the derivative, because when we have a horizontal tangent, our slope should be 0. So let's investigate a little bit further. Let's look at between this vertex and this one, or between that maximum and that minimum value. On that interval from negative 3 pi over 2 all the way up to negative pi over 2, we see that sine of x is decreasing. And if sine of x is decreasing, its derivative should be negative throughout that entire interval. And looky here, cosine is actually negative throughout that entire interval. So that's just a quick justification to show you how the slope of the sine curve is actually equal to the y-coordinates on the graph of the cosine curve. Similarly, that's a hard word to say, we can look over at the second graph here. And in this time, the blue curve is cosine. So that's our sort of original function y. And the red function that I've graphed here is negative sine. So if we look at all those places where I have horizontal tangents on the cosine curve, I see the red curve, which is the negative sine, is actually equal to 0. So that would make sense. Also, let's look at one of the intervals where we go from one vertex to the next, or from one extreme value to the next. So from that local min to that local max, what we can see is that our cosine curve is increasing all the way through from negative pi to 0, and we can see that the sine curve, or sorry, the negative sine curve, is actually positive all the way through, which seems to jive. That's not a proof, that's just a bit of a conceptual demonstration to show you how all this stuff fits together nicely in our brains. Okay. Now that we have the derivative of sine and cosine established, let's see if we can figure out the derivative of some of our other trig functions. So how about secant? How are we going to find the derivative of the secant? Well, since I know about sine and cosine, and it doesn't say we have to use the identity here, it just says differentiation rules. Okay, so for secant, I know that that's actually equal to 1 over the cosine of x. So if I wanted to differentiate that, knowing already what the derivative of cosine is, I could use a quotient rule, which would be a little bit of overkill here, because it's going to be much easier just for me to change this to cosine of x. And notice that I'm using big brackets outside here to say -1. This is not inverse cosine, it's just the reciprocal of cosine. So if I'm going to differentiate that, f prime of x is going to be a power function on the outside and a trig function on the inside. So I need to use my chain rule. So it's going to be negative outside of cosine of x to the power of -2. So I multiply by the exponent and reduce it by 1. Then I have to multiply by the derivative of the guts here, and the derivative of cosine is negative sine x, as we just saw. Okay, so I'm going to try to simplify this then. So if I try to simplify that expression, I can say that f prime of x is equal to, so a negative times a negative will go away, so I'm going to have a positive. And if I don't want to have negative exponents, I'm going to say that my numerator could be sine x, and then my denominator could be cosine squared x. So if you wanted to leave it in terms of sine and cosine, that is a derivative for secant. But that's not usually the way we represent it. We usually like to represent these things without fractions. So in order to do that, we sometimes play this little funny trick where we say this is 1 over cosine x times sine x over cosine x. which is the same thing as what we have up here. All right, so when we have that, then we just change those into some trig functions that we recognize. So 1 over cosine, of course, is secant x, and sine over cosine is tan x by tan x. All right, so the derivative of f of x equals secant x is f prime of x being secant tan. Fun. Okay, let's move on to another one. Okay, this time we want to use a quotient identity in differentiation rules to find the derivative for tan x. All right, let's try this. Quotient identity tells me that tan of x is actually equal to the sine of x divided by the cosine of x. Okay, so this time I'm going to have to use quotient rule to get anything sensible out of this. So let's say f prime of x equals. So quotient rule tells me I differentiate my numerator, which will be the derivative of sine being cosine, and then I multiply that by the denominator, which is also cosine, so that'll be cosine squared. And then I subtract. The derivative of my denominator is negative cosine, so we'll say negative, subtract the negative is going to be minus, so it becomes plus sine, and multiply that by the numerator, which is already sine, and we have a sine squared up top. So all of that has to be divided by the square of our denominator, which is cosine, so cosine squared. And if you've got your identity hat on, you notice right away that this stuff up here, cosine squared plus sine squared, is the first Pythagorean identity. So that tells me that f prime of x here should actually be equal to 1 divided by the square of the cosine function. Okay, well, if I want to write that as not being a fraction, I'm going to think of 1 over cosine as being just secant. So that tells me that f prime of x is equal to secant squared x. And then we have our derivative for the tan function. Okay, not so bad. Alrighty, so we're going to jump right into the your turn stuff here. Not a lot of detail here. We just want to make sure everybody gets these down right and know how we get them. So it says to use trig identities and differentiation rules to find the derivatives of each function. Write your answers in a simplified form with no fractions. So try to write them in terms of trig identities so that you don't have any fractions, because those are the forms that we usually refer to when we talk about the derivatives of our trig functions. All right? So give that a whirl and see what you come up with. I'll jump now, and here's the solution for that. So it turns out that the derivative of cosecant is negative cosecant cotan, and the derivative of cotan is negative cosecant squared. All right, so I want to take a minute now to look at the summary of this stuff, because it says you should be able to derive the derivatives of sine x of the sixth primary trig ratio. So we just did that. And it's also valuable to commit these to memory. You really should memorize them because it's going to make your life a lot easier instead of having to rederive them every time you need them. But I want you to notice something about all of these trig derivatives that we have here. And it's one way that I sort of look at it to help me remember what's going on. So start by looking at all of the trig identities, or sorry, all of the trig derivatives for the original functions that start with a letter other than c. So if I look at y equals sine x, its derivative is cosine. Tan x has a derivative of secant squared, and secant has a derivative of secant tan. Okay? Then we're going to look at the co-functions, or their partners. So the co-functions here are just the sort of counterparts for each one. So the derivative of cosine is the same thing. It's the opposite of what we had before. It's sine, but it's negative. The derivative of cosecant is actually very similar to the derivative of secant, except instead of being secant tan, it's cosecant cotan, and it's negative. And the derivative of the cotan function is very similar to the derivative of tan, only instead of it being secant squared, it's cosecant squared, and it's negative. So there's a lot of symmetry sort of in the way that these come together, so it makes them easier to memorize. And you'll notice that the derivatives of all the co-functions, or anything that starts with the letter c, has a negative derivative. Okay, so I hope that's helpful. We're going to look at some more complicated derivatives with trigonometry in our next session. So hopefully we'll see you then, and if you have any questions, put them up on D2L. Good luck studying.